Hi friends, in today's video I'm going to talk about hydrohalogenation of alkene. The hydrohalogenation is the addition of a hydrogen, and halogenation to an alkene. So most of the time it's performed with chlorine, bromine and iodine, and rarely with fluorine. So here we have an hexene, we add to it a hydrogen and bromine in order to perform the hydrohalogenation. So let's talk about the mechanism here. Here we have 1, 2, 3, 4. So here we have a butene. We add, without including the methyl, we have a butene. We add to it a hydrogen and a bromine atom. If you can see here, the hydrogen is partially positive and the bromine is partially negative. The reason for that is that bromine is very electronegative, so it's pulling the electrons of the bond toward it, leaving the hydrogen positive. So here we have the double bond, which is acting as a nucleophile, meaning it's negative. It's going to grab the hydrogen, which is positive, from this bond here. We have a proton transfer. When it comes to grabbing hydrogen, it's a proton transfer. Here we have a hydrogen which is moving to this bond, this alkene, and bromine, which is electronegative here, leaving it alone. And in the second place, we have a carbocation. A carbocation meaning that we have a carbon with insufficient number of bonds. Here we have 1, 2, 3, and as we know, the carbon needs 4 bonds. So here it's lacking 1 bond, making it positive. And what's gonna happen here is that bromine is going to attack the carbocation in order to increase the stability of the alkene. So it's gonna be attached to the carbocation here. So here we have two main options. The first option is attaching the bromine to the tertiary carbon here and attaching the hydrogen to the secondary carbon here, or the opposite, attaching the hydrogen here and the bromine here. Let's explain this detail here. So here for carbocation, we have the primary, here we have secondary carbocation because we have 1 bond and 1 bond, so it's a secondary carbocation. And here we have a tertiary carbocation, 1, 2, 3. So as we know, the carbocation is very stable. It's more stable than the secondary carbocation and more stable than the primary carbocation. So here we have, most of the time, according to what's called Markovnikov rules, always the halogen is attached to the carbon which is the most stable, meaning it's attached to the carbon which is like tertiary if we have an option, and if you had to choose between the primary and the secondary, it's going to be attached to secondary carbocation. For this reason, it's attached here and here. Like this is a tertiary, it's more stable because it's more substituted here. And the hydrogen is attached to the less stable, which is the secondary carbon, and which is the less substituted. That's called the Markovnikov addition. So when it comes to hydrohalogenation, we have to follow the Markovnikov addition, except in one case, except when the bromine atom and only the bromine atom is reacting with an alkene, but in the presence of an alkyl peroxide, which is represented as ROOR. So whenever you see an alkyl peroxide, like with the hydrogen and bromine acting with an alkene, you have to do what's called the anti-Markovnikov rule, which means that the hydrogen is going to be placed on the most stable carbon and the bromine is going to be placed on the least stable carbon here, as you see. So let's summarize. Hydrohalogenation is the addition of a hydrogen and a halogen to an alkene. We have two main steps here. we have the proton transfer in the first place and the nucleophilic attack in the second place. Let's talk about thermodynamic here. When it comes to thermodynamic, we have three main steps. The first one is the reactance here, and then you have the transition state, which is the formation of the carbocation, and then you have the nucleophilic attack, which gives us this product here. And this reaction is called radioselective. It's radioselective, meaning that the bromine or the halogen, it's always placed on the most stable carbocation, except when it's reacted with the alkene in the presence of alkyl peroxide here. And let's talk about stereochemistry here really quick. So for stereochemistry of hydrohalogenation, we have here this example 1, 2, 3, 4. So here we have a butene, we add it an HCl, and here we have, this is the carbocation. When we break this bond, we have the proton transfer. It's gonna grab the proton and leave the Cl minus. And here we have, this is the carbocation. It's a secondary carbocation here, meaning that the chlorine is going to be bonded to the secondary carbocation, not to the primary one. Hydrogen is going to be bonded to the primary. And here, since it's bonded to secondary carbocation, we have two options. The chlorine can attack this carbocation from this side, or it can attack it from the other side. We have two main options. So if it attacks it from this side, like from the front of the page, it will be an R configuration, since the priority is for chlorine going this way, and the hydrogen is in the back, so it won't affect the configuration. And if it attacks it from the behind, from the back of the page, we have the S configuration, because the hydrogen here, it will be in the front of the page. So this is the hydrohalogenation. Thank you.